Welcome to Recitation session for fluid mechanics. This is week 12. This week we will have 4 questions, and these are questions from chapter 9. So let's get started with the first question. This is 9.3. Here we have a boat 3 feet by 3 feet that weighs 32 pound-force, and it slides down on an inclined ramp with a velocity of 0.6 feet per second. The boat is separated from the ramp by a layer of oil, 0.02 inch, which is this one, this oil layer. And we need to calculate the dynamic viscosity of the oil. So let's look at the question. Here we need to calculate the dynamic viscosity. So to find that, we need to write directions in this question. So we will have shear force, and we will use some equations. So let's see what we have. First of all, of course, we will have weight, which is acting vertically. And because of this weight, we will actually have sinus component of this weight, because this is the direction of the movement. And this system will also have a viscous shear force, which acts on the opposite direction of the moving. So the main action of this viscous shear force is resisting to the motion. So this means we will have a shear force which is the opposite of the move. So this means we will have weight in this direction, and it should be equal to shear force. So when we say shear force, it is the force that acts tangentially. So here we can see that it is acting this boat tangentially. So shear force is, let me write Fs, is calculated with this equation, which is shear stress times area. So in other words, it means it is the force on area due to this shear stress. And shear stress is proportional to the velocity gradient, like explained here. And this is actually Newton's law of viscosity. So this actually explains the change of shear stress with the velocity change. And here, this is actually position measured from the wall. So in our case, it is going to be the thickness of the oil layer, because this is the distance from the wall, and we had 0.02 inch of oil layer, and it is the distance between this boat and this wall. So this is the shear stress formula, And we can actually write it in another form. So let me continue from here. We can actually write it like velocity over the distance. So let me write delta y. And since we said this is equal to shear force, this will be equal to dynamic viscosity times velocity gradient times area. And in our case, the area is actually L squared because we are calculating that area, and it will be L. This is the dimension of the board, which is 3 feet. So this is our main formula. So let's see what we need. Here we need to find sinus theta. So we have an angle here. So here sinus theta will be equal to 5 divided by 13 because this is hypotenuse and we have 5, 12 and it will be 13. So in this case, if we leave the dynamic viscosity alone, we will get weight, sinus component of the weight, L square, the distance from the wall, and the velocity. And this will make our question. Actually, right here. The weight was 32 pound force, so we have 32 lbf. The sinus is equal to 5 divided by 13. L square is the dimension of the board, so it is actually 3 square. The distance from the wall was 0.02 inch, and since all other units are in feet, we will be converting this inch to feet. And lastly, the velocity is 0.6 feet per second. And from here, the dynamic viscosity will be equal to 0.0038 pound force second over square feet. So what we did is we calculated all the forces within the moving direction. So we only have sinus component of weight, and we have the viscous shear force, which resist the motion, so that these are actually equal to each other because we don't have any other force. So we started the calculations with the shear force, and it is shear stress on the area. So the shear stress is coming from Newton's law of viscosity, and it is actually showing the relationship between the shear stress and the velocity gradient with the constant dynamic viscosity. And here, u was the velocity and y is the position measured from the wall. So that using this equation, we connected it like this one. Then we calculated area, which is given in the question, which is 3 feet length. So for the area, we calculated it as L square. And then since we have this relationship, we needed to just leave the dynamic viscosity alone. And after that, we substitute everything, then we get the final dynamic viscosity value. Okay, let's continue with the second question. This is 9.6. Here we have a flat plate which is pulled to the right at a speed of 30 centimeters per second, and oil with a viscosity of 4 Newton second per square meter fills the space between the plate and a solid boundary. The plate is 1 meter long by 30 centimeters wide, and the spacing between the plate and boundary is 2 millimeters. So this means that we have a fluid with like oil, and it has viscosity, and it is filling that space between these two plates. So this is solid boundary, and we have a moving plate here. The length of the plate is 1 meter and its width is 30 centimeters. And the spacing between the plate and the boundary is 2 millimeters, which means 0.02 meters. And lastly, the velocity is 30 centimeters per second, or 0.3 meters per second. So we need to express the velocity mathematically, and we also need to find if the flow is rotational or irrotational. And lastly, we will check if the continuity is satisfied, and we will calculate the force required to produce this plate motion. So here we have a situation. So we have a viscous fluid between two plates, like plate 1 and plate 2. And one of them is moving tangentially relative to the other. So we define this kind of flow as quiet flow, and it has this relationship between the velocity and the distance. So in other words, we can say the velocity profile is linearly changed with y. So in your lectures, lecture 20, on page 3 and 4, you will see that figure. So it is actually representing quiet flow, and it also gives that relation in the slides. So here we have a velocity distribution, and this is capital U, or it is maximum velocity. And at the bottom, we have zero velocity. And here L is actually delta y, which shows the vertical distance between the bottom plate and the top plate. So since we need to first express the velocity, we will be using this relation. And as I mentioned, the capital U is maximum velocity. So U is U max y and delta y. So here, as I mentioned, this is showing the velocity profile, change in velocity profile with y. So U max is given as 0.3 meter per second times y, and delta y is that distance between two plates, or it is this distance. So it is given as 2 millimeter or 0.002 meter. And this gives u as 150 y meter per second. So based on the value of y, so for example, if it is 0, of course this velocity will be 0. Or if it is max, we will get the length of the distance of y times 150. So this is the first thing that question asks. So let me write A. In question B, it is asking if the flow is rotational or irrotational. So you may remember that from our previous slides, but for irrotational flow, we need to satisfy this relationship. So partial derivative of u with respect to y is equal to v over x. So the derivative of u with respect to y is 150, which is coming from here. But we don't have any v term, or we don't have any vertical velocity. So this means we have 0 here. So these are not equal. So we have irrotational flow. In question C, it is asking if the continuity is satisfied using the differential form. So for that, we need to satisfy this differential form. And if you look at terms, I also forgot to mention, since we don't have any vertical movement, we will have 0 velocity vertically. So this is directly 0. And that's why we had 0 here. So here, there is no x term in u. So it is 0. And also v is also 0. So we will get 0 plus 0 equal to 0. So this means continuity is satisfied. And lastly, we need to calculate the force to produce this plate motion. Again, this is a shear force, so we have shear stress times area. And the shear stress was from previous question. We will actually use the same thing, so we can directly use that. Viscosity, velocity over the thickness. Times area. So here the viscosity is 4 Newton second per square meter times the velocity was given as 0.3, and the area is 1 multiplied by 0.3. This was length and this was the width of the plate. So when we divide it by delta y, which will be this distance or this distance, so it is 0.002. and this gives 180 Newton. This is question 9.16. Here we have two horizontal parallel plates spaced at 0.015 feet apart. So the pressure decreases at a rate of 25 psf per feet in the horizontal x direction in the fluid between these two plates. So what is the maximum fluid velocity in the x direction? And the fluid has a dynamic viscosity of 10 to the power of minus 3 and a specific gravity of 0.8. So here we don't actually have a moving plate, so we have two stationary plates. And you can actually see that in your lecture 19 and also in textbook. Textbook page 297. So we need to find the maximum velocity. So you can use equation 9.20, which gives u maximum is equal to b square. B is 0.015, so it is actually this distance. Eight times of dynamic viscosity, d over ds. So this part is actually the change of piezometric head with location. So since the question says we have horizontal plates, there is no change in the elevation. And I can write this as h, which is piezometric head. So we can actually simplify this question like this equation like b2 square dp over ds. So the change of pressure within the distance, within the given distance. So for example, we can say from this part to this part, we have 25 psf per feet change in the pressure. So this means we actually have 25 pound per cubic feet. And this is actually coming from the PSF, which is pound force per square feet. And since the pressure decrease rate is 25 psf per feet, then we will get pound force per cubic feet. So let me write everything we have to calculate the U max. B is the distance between these two plates. So it is 0.0015 feet. We have 8 times of dynamic viscosity. And we have 25. From here, maximum velocity between these plates will be 0.7703 feet per second. Sorry. In our final question, which is 9.17, we have these plates, and we have viscous fluid that fills the space between these two plates. And the pressure at A and B are 150 psf and 100 psf. So we have A and B. This is 150 psf and this is 100 psf. And the fluid is not accelerating, which means no change in the velocity. So we have a constant velocity. So if the specific weight of the fluid is 100 lbf per cubic feet, we need to conclude if the flow is downward, upward, or if there is no flow. So the best way to understand the flow direction is comparing piezometric heads, because the fluid will move in direction of decreasing piezometric head. This means we have a total, let me write it. Since the flow is will be moving from higher head to lower head, we are comparing with piezometric head. So let me write HA the pressure of A divided by its specific weight plus the elevation. So we have 150 psf and 100 for the specific weight plus 0. So we can actually take point A as the reference as 0. And for the B, we will be using the same equation. So for B, we have 100 psf divided by 100. And for the elevation of B, which is ZB, we are going to use trigonometry, so we cannot directly take this 2 feet because it is actually the distance between point A and B. It is not its vertical elevation, so that we need to get these lines distance. So we have 30 degree here, and let's say this is ZB. ZB will be equal to 2 sinus 30, and it will be 1 feet. So this gives 1.5 feet, and this is going to give 2 feet. So here, HB is higher than HA. So the flow is from B to A. So it is actually downward.